I am Carmen Estevez. I work at the Catalan Institute of Nanoscience and Nanotechnology, and I am a tenure scientist. Our work is the development of a nanophotonic biosensor platform for the multiplex detection of different pollutants in water treatment plants in the NIAGARA project. The Catalan Institute of Nanoscience and Nanotechnology is located in Barcelona, in the campus of the Autonomous University of Barcelona in Bellaterra. And the main focus of its global research is the application of nanoscience and nanotechnology from simulation, from fabrication and application of nanomaterials in three main pillars, which are health, energy, and communications. And our group, the Nanobiosensors and Bioanalytical Applications group, has been devoted his whole research for the last 20 years in developing photonic technology to achieve biosensors, optical biosensors, with the main goal of reaching point-of-care devices, integrated devices to be applied in clinical diagnostics and environmental monitoring. In the NIAGARA project, the role of the nanobiosensors and bioanalytical groups is the developing of a multiplex nanophotonic biosensor for the detection of up to 4 pollutants found in drinking waters. The main challenge of detecting pollutants in water usually are related to two main aspects. One is the sensitivity that you need to achieve, because there are some levels that has to be reached, and usually those are low, especially in the according to the European legislation. And the other aspect that is really crucial is to provide not continuous, but close to continuous monitoring of the quality of waters. And this requires to perform analysis during short periods of time. And currently this may be done with chromatographic methods, which usually requires taking samples out of the water sampling and take it to external analytical laboratories, which eventually the whole process may be too long. Okay, a biosensor is a device, is an integrated device which allows you to monitor a specific substance that you want to analyze. A very typical example that helps everybody to understand what a biosensor is the typical glucometer that all the diabetic people use to monitor the glucose levels in blood. So from this, you can find different kind of devices which may monitor different kind of substances, from small molecules like glucose to big entities like cells or bacteria or viruses, or other kind of markers like proteins and small drugs. In the NIAGARA project, the type of biosensors that we developed is an optical biosensor, is specifically a nanophotonic biosensor which rely on structures that are fabricated in silicon, which incorporates waveguides, very small, tiny structures on its surface, in such a way that it can incorporate different receptors, different antibodies, which is going to be the element that is going to give you the specificity for detecting the different pollutants that are included in the project. The biosensors that we employ in the NIAGARA project rely on silicon photonics technology. So we have structures that are based on silicon nitride, which are fabricated in clean rooms with very clear specifications. And we employed in one chip different waveguides, different sensors that are incorporated in a single chip, in such a way that we can incorporate different receptors, one per each kind of target that we want to detect for each pollutant. And what we monitor is changes in the light that is traveling through the surface of this sensor. So when we have an antibody mobilized on the surface and we detect our analyte of interest, there's a small change in the light property, in the properties of the light that is traveling through the surface. This is what we can monitor in real time. This is a huge advantage because we can really follow in real time how the interaction is taking place. So we can have an analysis time as short as few minutes. In the NIAGARA project, we aim to implement a multiplex biosensor which provides the simultaneously detection of different pollutants at the same time. This is not an easy task because usually when you monitor, analyze, or any kind of target, it's usually done individually by different techniques. In the case of pollutants, usually different chromatographic methods may be employed for detecting each one of them with its own process or protocol optimized previously. So we aim to integrate everything in one integrated device, a small compact device that can be deployed in the drinking water treatment plants in such a way that can allow the monitoring at particular times, close to real time, to be sure about the levels of the pollutants in waters. The nanophotonic biosensors that we developed, one of the main characteristics they have is the extremely low sensitivity that they can reach. This is because of the working principle, which is based on the evanescent field detection, and actually it can measure very small, very minute changes in refractive index units, okay? This translates if we can develop and optimize the whole process and in the way that we put the antibodies and the analytical process that we employ for detecting each interaction event. This usually can translate in detectabilities, in limits of detection, in the picomolar range. So this is really, really competitive with other techniques, conventional techniques like chromatography, liquid chromatography or gas chromatography, but in the sense that we minimize any kind of sample treatment because we can employ directly water samples that can be delivered directly to the surface. And at the same time, we can get the results in few minutes. So all of these kind of characteristics make this kind of biosensors really, really competitive in the field of environmental monitoring and also in other areas. The technology, the optical technology, nanophotonic technology that relies in this kind of sensing has a huge market, not only in the environmental monitoring, which is crucial, but also in other kind of diagnostic, let's say diagnostics, I'm already introducing that. So in clinical diagnostics, okay? You can eventually have instruments, portable, integrated instruments that incorporate these kind of receptors, this antibody that gives you the specificity that you want, the sensitivity that you need for analyzing real samples, not only waters, but also blood, urine, other kind of biofluids in the field of clinical diagnostics, close to the patient, let's say, for instance. You can deploy it to a water treatment plant, you can deploy it to a hospital, to an ICU unit, to monitor different biomarkers, different parameters in a patient. So you accelerate, you improve, and you somehow improve the management of diseases from different perspectives. Getting the results out of the centralized laboratory, shorten the time of analysis, and so on. So the field of point-of-care diagnostics, which cover our technology, is huge, and it's evolving rapidly. This started, it didn't start, but it made a huge leap after pandemics, and the trend is the same. It's increasing, it's moving towards this kind of technologies, not only optical, but other kind of technologies that provide this rapid response and at affordable cost, which can contribute to improve detection.